So part 4 of mathematical methods in physics. Let's start with problem 7 here. Starting from Bessel's equation, x squared y double prime plus x y prime plus quantity x squared minus nu squared y equals 0. Part A, derive the Frobenius recursion relation. Part B, construct j sub nu of x. Part C, show explicitly that for half integer order j sub 1/2 of x reduces to elementary functions. And part D, derive asymptotic behavior as x approaches infinity using dominant balance arguments. So this is a special functions problem. Bessel's equation, x squared y double prime plus x y prime plus x squared plus nu squared times y there. That equals 0. We're going to use Frobenius form. Y equals that sum from m equals 0 to infinity, a sub m x of m plus s. Then here y prime equals this sum from m equals 0 to infinity, a sub m parentheses m plus s x to the m plus s minus 1. Y double prime equals this sum m equals 0 to infinity, a sub m times m plus s times m plus s minus 1 times x to the m plus s minus 2. And this is, sorry about that, that's an S. Substitute this sum a sub m bracket quantity m plus s squared minus nu squared close bracket times x to the m plus s plus the sum a sub m x to the m plus s plus 2. Adding those together, that yields 0. So the in this yield equation is s squared minus nu squared equals 0. So s equals plus or minus nu. Some call it indicial, some call it indicial. So choosing s equals nu, the recursion relation becomes a sub m times the quantity m plus nu squared minus nu squared close bracket plus a sub m minus 2. That equals 0. So that's for the recursion relation, and thus a sub m equals negative this quantity a sub m minus 2 over m times the quantity m plus 2 nu. And building on that here, what we could say is the odd coefficients, they vanish if a sub 1 equals 0. So a sub 2k equals negative 1 to the k a naught over 2 to the 2k, k factorial times nu plus 1 times nu plus 2, on and on to the nu plus k term. So choosing a naught equals 1 over 2 to the nu gamma nu plus 1. Then j sub nu of x equals this sum k equals 0 to infinity times this negative 1 to the k over k factorial gamma k plus nu plus 1 times this x over 2 to the 2k plus nu. So for nu equals 1/2, we could say this j sub 1/2 of x equals square root of 2 over pi x sine x. And as x approaches infinity, the leading oscillatory asymptotic form is j sub nu of x is asymptotic to square root of 2 over pi x times cosine of x minus nu pi over 2 minus pi over 4. So that's number 7. Moving along now to number 8. For number 8, we want to find the extremal curve minimizing the functional j of y equals this integral 0 to 1 square bracket y prime squared plus xy plus y squared close bracket dx. Subject to y of 0 is 1, y of 1 is 0. So for part A, we want to derive the Euler-Lagrange equation. And for part B, solve the resulting boundary value problem. For part C, determine whether the extremum is minimum or maximum. Part D, what we want to do there is use second variation analysis to justify answer. So this is a calculus of variations problem. So here, functional j of y, that equals what we were given up here. Okay, subject to these conditions. So the Lagrangian is going to be f equals y prime squared plus xy plus y squared. So the Euler-Lagrange equation is going to be the partial of f with respect to y minus the derivative here with respect to x, partial f with respect to y prime, that equals 0. So here the derivative of x here times partial f with respect to y prime equals 0. So derivative here of partial derivative here of f with respect to y equals x plus 2y. Partial derivative of f with respect to y prime equals 2y prime. So this d dx 2y prime, that's going to be 2y double prime. So x plus 2y minus 2y double prime equals 0. And simplifying that, y double prime minus y equals x over 2. Okay, so picking up with this, if we solve this, y sub h equals c sub 1 e to the x plus c sub 2 e to the negative x. We try a particular solution, y sub p equals ax plus b. Then y sub p double prime minus y sub p equals negative quantity ax plus b, and that's going to equal x over 2. So negative a is equal to 1/2, then negative b is equal to 0. So a equals negative 1/2 and b equals 0. So from there, y equals c sub 1 e to the x plus c sub 2 e to the negative x minus x over 2. Y of 0 is 1, where c1 plus c2 is 1. Y of 1 is 0, c sub 1 e plus c sub 2 e to the negative 1. That's a minus 1/2, sorry, equals 0. So c sub 2 is 1 minus c sub 1, and then c sub 1 times the quantity here, e minus e to the negative 1 plus e to the negative 1 equals 1/2. So c sub 1 equals 1/2 minus e to the negative 1 over e minus e to the negative 1. And c sub 2 equals 1 minus c sub 1. So the extremal is y of x equals this quantity 1/2 minus e to the negative 1. Sorry, that's a 1/2. So 1/2 minus e to the negative 1 over e minus e to the negative 1 times e to the x plus parentheses 1 minus 1/2 minus e to the negative 1 over e minus e to the negative 1 times e to the negative x minus x over 2. So our second variation here, that's a delta squared j equals this integral from 0 to 1, bracket 2, here eta prime squared plus 2 eta squared, close bracket dx, where eta of 0 equals eta of 1 equals 0. So since delta squared j is larger than 0 for all non-zero admissible eta, the extremal is a strict minimum. Okay, so that is part 4. Thank you very much and have a great day.